Okay, so let us continue the session. I see that the next speaker is here. Let me introduce Parth Chavan, Euler circle Nashik, with the talk Hurwitz zeta functions and Ramanujan's identity for odd zeta values. Please.
Thank you. Thank you. Let me just share my screen. So first of all, I would like to thank the organizers for inviting me to this conference and allowing me to be a part of this amazing conference. So my presentation will be centered around Hurwitz zeta functions and Ramanujan's identity. And one of the goals of this talk would be to convince the audience that the Ramanujan's identity is an amazing identity and it's beautiful. Give me a second. Okay. So the first of all, we will introduce literature on the Riemann zeta function, its special values, and introduce some more modular relations. We will also provide some generalizations of existing modular relations for the Hurwitz zeta function. The Riemann zeta function is defined by this infinite series, sum over 1 to the n to the s from n equals 1 to infinity. However, this series converges only when the real part of s equals 1. However, the Riemann zeta function can be analytically continued to the whole complex plane using some contour integrals. And it extends to a meromorphic function with zero simple poles at with simple pole at s equals 1 and zeros on the line s equals 1 by 2 and at negative even integers. We now introduce Bernoulli polynomials. Bernoulli polynomials are defined by this generating function z e to the xz over e to the z minus 1, which equals some bn of xz to the n over n factorial. And Bernoulli numbers are defined by Pn of the Bernoulli numbers are just the evaluation of Bernoulli polynomials at x equals 0. Euler proved that in the 18th century that the value of zeta of 2n is this expression, which was also related to the famous Bessel's problem. He evaluated this expression by considering the power series expansion of sine x by x. Well, this also proves that the Riemann zeta function at even arguments is transcendental since pi is transcendental. This naturally raises the question of finding whether odd zeta values are irrational. However, the only known result about this is the result by Aperi, who proved that zeta of 3 is irrational. Apart from this, Riemann and Ball-Riemann also proved that infinitely many odd zeta values among the set z of 3, z of 5, z of 7, and so on are irrational. Well, this isn't a very strong result, but it still is one of the best results concerning the irrationality of odd zeta values. This is also a folklore conjecture for odd zeta values, which is to prove that the numbers pi, zeta of 3, zeta of 5, and so on are algebraically independent. We now state Ramanujan's identity for zeta of 2n plus 1, which is for alpha and beta any positive real numbers which satisfy alpha beta equals pi square and n any non-negative positive integer, then this identity holds. Notice that this Lambert series converges very rapidly, and thus this identity allows us to accurately approximate the odd zeta values. This is also a great result in computational complexity since the computation of odd zeta values is a little difficult. So this provides a series acceleration formula for odd zeta values. As a consequence of Ramanujan's formula, when we plug in alpha equals beta equals pi and n equals 2n plus 1, we get the following identity for zeta of 4k plus 3, which was also found by Lurch in the 19th century. Notice that to prove that zeta of 4k plus 3 and pi are algebraically independent, it only suffices to prove that this series is algebraically independent with respect to pi. Well, now there also lies an intimate connection of Ramanujan's identity with Eisenstein series, which I would like to highlight. The Eisenstein series of modulus 2k for tau is defined by this infinite series, some m common in the set of z cross z, 1 by m plus n tau is to 2k. There is also a alternate expression to express this Eisenstein series as 2 times z of k times 1 plus c2k, where c2k are coefficients given by z of 2k by pi, and sigma 2k minus 1 is the divisor function, which is sum over d completed divides n d to the 2k minus 1. This gives us that the Lambert series, sum n to the k over e to the n y minus 1, can be essentially considered as the Eisenstein series on the special linear group with respect to the integers. Well, why this result is important is because this series also appears in Ramanujan's identity, and thus Ramanujan's identity can be considered as a transformation formulae for Eisenstein series. Let f of z equals this sum m to the minus 2n minus 1 over e to the alpha m minus 1, alpha to the minus n, which was just considered over here. So this is essentially an Eisenstein series. And what Ramanujan's identity tells us is that z to the n f of z minus f of 1 by z can be expressed as an error function, where epsilon of z is the convolution of Bernoulli numbers. Thus, this connection reveals that the Ramanujan's identity can be considered as a transformation formulae for the Eisenstein series. We now introduce the Hurwitz zeta function. For real part of s greater than 1, the Hurwitz zeta function is defined by this infinite series since it only converges for a real part of s greater than 1. However, the Hurwitz zeta function can be analytically continued to the whole complex plane using counter integration techniques. It also has a symbol pole at s equals 1, and apart from that, it is meromorphic and entire. Now, a natural question is to find the Ramanujan type formula for the Hurwitz zeta function. We answered this question in our paper and gave several Ramanujan type formulae for convolution of Riemann zeta Hurwitz zeta functions. We first introduced Hurwitz kernels. Ramanujan kernel can be expressed as this contour integral. It can be noticed that the function 1 over e to the 2 pi x minus 1 also appears in Ramanujan's identity for odd zeta values, and it actually turns out that it can be expressed as this inverse Mellin transform. We integrate over the line C, where C is any arbitrary real number in the interval 1, 2. Motivated from this, we introduce the Hurwitz kernel, which is defined by this contour integral. It can be noticed that this function psi of x comma 1 is actually the Ramanujan's kernel. So this refinement of the Ramanujan's kernel will be actually very interesting, which will be demonstrated in the next few slides. To explicitly evaluate this counter integral, we shift the line of integration to negative infinity and correct the corresponding residues at poles, which are just minus 2kp plus 1, where p is the set of natural numbers. And it actually turns out that this integrand goes to 0 as the imaginary part of s tends to infinity, which can be proved by considering Stirling's approximation for the gamma function. Using this, we now prove the convolution of Hurwitz zeta function at even integers, and it can be noticed that when we plug in A equals B equals K equals 1, we get Ramanujan's identity for odd zeta values. One particular thing I would like to highlight is that this kernel psi alpha of n plus b a k cannot be considered as Lambert series. Thus, this identity is not connected to the Eisenstein series, as the Ramanujan's identity is connected to Eisenstein series. As a proof of as a sketch of the proof of this identity, we can write the sum psi alpha of n plus b a k over n plus b to the 2k n minus plus 2k minus 1 as this contour integral. And this integrand tends to 0 as the imaginary part of s tends to infinity. And thus we can exploit this to shift the line of integration to minus c minus 2k and minus 1 and use residue theorem to collect the residues at corresponding poles. And after we shift the line of integration to minus s minus c minus 2k and minus 1, we can use these change of variables s2 minus s minus 2k and minus 2k plus 2 to explicitly evaluate this integral as 1 over as a function over beta of pi. Thus, we can use this transformation formula to explicitly prove this identity for Hurwitz zeta function convolution at even integers. Now, a natural question is to find the Ramanujan type formula for convolution of Riemann zeta function at odd integers. It was answered by A. Dixit et al. To be this convolution formula. Now, A. Dixit considers the kernel integral over a real part of s equals 1, zeta of 1 minus s x to the minus s over 2 sine pi s by 2. This can similarly be evaluated by shifting the line of integration to negative infinity and collecting residues at corresponding poles, and which gives us this partial fraction expansion. We now refine the odd Hurwitz kernel as we had refined the Ramanujan kernel. The odd Hurwitz kernel is defined by this contour integral on real part of s equals some number between 1 and 2, zeta of 1 minus s comma a over 2 sine pi s by 2k x to the minus s ds. Its partial series expansion can be similarly given as the partial series expansion of the odd zeta kernel just by shifting the line of integration to negative infinity and collecting the residues. Similarly, as the convolution identity of a zeta function at even integers, we can now give convolution identity of a zeta function at odd integers, which is this identity. Notice that when we substitute a equals b equals k equals 1, we recover A. Dixit's identity for convolution of Riemann zeta function at odd integers. Thus, this gives us a 3-parameter generalization of A. Dixit's identity. Now, a natural question would be to find a Ramanujan type formula for convolution of Riemann zeta function at odd and even arguments. This was also answered by A. Dixit, and they computed the Ramanujan type formula for a convolution of Riemann zeta function at odd and even integers to be this identity. Now, it can be noticed that this is just the odd zeta kernel, and this is the Ramanujan's kernel. And now we wonder whether such a transformation formula exists for Hurwitz zeta functions for the kernels phi and psi. This can also be positively answered, and the formula turns out to be this expression. And when we substitute A equals B equals K equals 1, we recover A Dixit's identity. To summarize our work in short, we generalize Ramanujan's formula and we give a 3-parameter generalization of several Ramanujan type identities that already exist in literature and generalize these for the Hurwitz zeta function. Now, a natural question arises, which is to find the Ramanujan type formula for zeta to the k of s. This question was positively answered by A. Dixit and R. Gupta for k equals 2, and it was evaluated to be this expression. They considered a similar counter integral to be this inverse mid-in transform. However, these results unfortunately cannot be lifted for the Hurwitz zeta function, as will be explained shortly. If we define the analogous kernel for Hurwitz zeta function to be this counter integral, the coefficients of the function zeta of 1 minus s comma a square are not actually simple, and this Dirichlet series cannot be explicitly evaluated for general A, but this can be evaluated for specific values of A. For instance, A equals 1 by n, where n is in the set of natural numbers. Now, I would like to end this talk by asking the audience a question: if we can use similar techniques to find general transformation formulae for any two arbitrary Dirichlet series, since this would allow us to find many transformation formulae, for instance, transformation formulae for L functions, etc. Thank you for your patience. I would like to open discussion for questions.
Thank you for interesting talk.